So thank you for staying, for those of you who are staying, and thank you for coming, for those of you who came. Today I will talk about a topic which has caused me quite a few sleepless nights. So let's start. The topic of the discussion is coin flipping. This is a joint work with Jeremy Hollon and Stéphane Weiss. And Jeremy Hollon is in the audience somewhere. It's right there. And Stéphane Weiss, he's not here. I would also like to thank Tobias Frietz, Nicolas Serre, and Matthew Brandijo for various useful discussions. So with that said, let me try to explain why, okay, I'll just take the mic out, it's a bit easier. Okay, so let me try to explain why coin flipping would be of any interest to a serious researcher, and I'm not saying that I am. So this is a slide from Professor Schaffner's talk last year at QIP. You see, it is something which is indeed studied. So, the usual scenario which is considered is key distribution in cryptography, and that's the situation where Alice and Bob, they trust each other, and they want to arrive. They want to make sure that their communication is protected against an eavesdropper. But what if they have a fight? Okay, so these are the kind of situations which are considered in what are called multi-party computation scenarios, where you have many players and there's a majority which is dishonest. Okay, and you still want to be able to do something worthwhile. That's the problem. It turns out that classically, unless you make computational assumptions, all of these are impossible. Okay, and obviously the question is, can you do something better quantumly? Turns out quantumly oblivious transfer and bit commitment can be shown to be equivalent, while classically they are not, as indicated by the blue implication. But that's as far as you get, because one can show that bit commitment is quantumly impossible, and thereby the entire hierarchy is also impossible. And so you see where I'm going with this. Coin flipping is not equivalent, and can we do it, whatever that is? And to be able to answer this question, let me start with defining the problem itself. So coin flipping is the following, so consider the following scenario. So Alice and Bob, imagine that they were friends at some point and they bought a very fancy car. And after some point they have a fight and they want to randomly decide who gets to keep the car. Okay? So more formally, Alice and Bob wish to agree on a random bit remotely without trusting the other player. Okay? There are two variants of this problem which are worth considering. The first one is called strong coin flipping. So in this, we assume that the players don't know the preferences of each other. So for instance, it could be that Alice always hated the car and Bob always wanted the car, in which case they wouldn't have to flip a coin. But since they do not know this in advance, they're anyway flipping a coin. Okay, so that is strong coin flipping. One could also consider weak coin flipping, where you assume that the players know the preferences of each other. So the previous case that I mentioned, where Alice does not like the car and Bob does, there would be no need to flip a coin. Okay, so that will never arise in a weak coin flipping scenario. Okay, since it's a cryptographic scenario where there are distrustful parties, it's important to consider the different scenarios that can arise. Okay, so I will call a player honest if the player follows the protocol exactly as described. Any deviation from it, and we'll call the player a cheating player. So the first case is when both players are honest, and in this we want the players to agree on the outcome, because remember, it's a protocol in which they're going to send and receive messages, and in the end they're going to arrive at a random bit. So we want both of them to agree on the final outcome that they receive. Okay? And we also want the protocol to be such that the probability of both players winning is equal, okay? That it's balanced in some sense. The scenario where Alice cheats and Bob is honest is where Alice can bias the outcome towards the value that she desires. And the protocol ideally should be such that it protects the honest player against the cheating player, which in this case would be Bob against Alice. Okay? And we can consider it the other way, when Alice is honest and Bob is cheating. Of course, there'll also be the case where both players are cheating, but since neither player is actually following the protocol, we will not be able to make any statement which depends on it. Okay? So this is a case we'll not consider. It's worth being a little careful with the definition of bias. So a protocol that solves the coin flipping problem is said to have a bias epsilon if neither player can force their desired outcomes with a probability greater than half plus epsilon. Okay, and here epsilon is, the half is just quantifying the fact that purely by chance one player will win, and epsilon is how much they can bias it. So now let's specialize to weak coin flipping. So remember, for weak coin flipping, the players will always have opposite preferences on the coin flip. Okay? If Bob wants heads, Alice wants tails. In this case, if both players are honest, I will denote the probability of Alice winning by PA and that of Bob by PB. If Alice is honest and Bob is cheating, I will denote the probability of Alice winning by P star A. And in the other case, when Alice is honest and Bob is cheating, I will denote it by P star B, the probability that the cheating player, which is Bob, winning. Okay? These are just some things that we'll use, so I'll just take a moment and introduce it. In terms of these variables, one can define the bias to be the smallest epsilon such that P star A and P star B are less than half plus epsilon, right? Because that's the maximum cheating that can be done. And it's very easy to obviously see that epsilon is bounded between 0 and half, and we would want epsilon to be 0 in the best case. Okay, so let's consider a very simple protocol to get a feeling for these numbers. So imagine the protocol is that Alice just flips a coin and declares the outcome, okay? So in this case, and imagine the coin is fair. So in this case, the probability that Alice wins would be half, right? And that should be clear. What about when Alice is cheating and Bob is honest? So remember, Alice is the one who's going to flip the coin, and Bob just has to accept the answer. So in this case, the probability that Alice wins is going to be 1, because she can just lie, right? So there's really nothing Bob can do. What about the other way? Well, what about when Bob is the one who's cheating and Alice is honest? By construction, the protocol does not give Bob any power. He just has to accept whatever Alice says. So in this case, the best probability of him winning is completely by chance, which is a half. Okay? So in this, there are two things that I would like to mention. First is that P star A and P star B can be different. Okay? They don't have to be symmetric. It depends on the protocol. And second, since P star A is 1, the bias in this case is a half. Okay? And it turns out, if you look at what has already been proven, that epsilon can always be shown to be half, regardless of which classical protocol one uses. Okay? And that is as far as we go classically without making any computational assumptions. And now we ask, what can we do quantumly? Quantumly, it turns out, Quantumly, it turns out that there is a distinction between strong and weak coin flipping. So for strong coin flipping, epsilon has been shown to be bounded below by this number, 1 by square root 2 minus half, by Kitaev at one of these QIP conferences, and apparently never published it. So people just, even today, just cite the conference and this lecture. As for an explicit protocol, the best we know is by Ambainis back in 2001, and that has a bias of 1/4. For weak coin flipping, it was thought that perhaps the same bound holds, but it was shown by Moshe, and later by Arnov and others it was verified, that the bias can be made arbitrarily small for weak coin flipping. If one assumes as a black box that one can implement weak coin flipping perfectly, it turns out that one can also do strong coin flipping optimally. Okay? But since we don't have the explicit protocol, we're still stuck with 1/4. As for an explicit protocol for weak coin flipping, epsilon has been shown to be 1 by 6. This is the best known protocol, again by the same author, Moshe, or Moko, I'm actually not sure about the pronunciation, sorry for that. Okay, so that is the state of the art. And the problem that I want to discuss here is precisely this. We want to find an explicit protocol that can actually go arbitrarily small, okay? Because we of course know we can go arbitrarily small. And to be able to discuss further, I would have to discuss some of the techniques which were used in proving that there does exist a protocol which can go arbitrarily small. So let's start with that. So Kitaev introduced 3 frameworks for studying coin flipping problems, which are all equivalent. The first one is how you define the protocol and analyze it. So this is in the usual language of quantum mechanics, which uses density matrices and unitary operators. Then there's something called the time-dependent point game picture. And then there's something called a time-independent point game picture. So these are words that I'll describe shortly. At the moment, I want you to know that there's a constructive way of going from a protocol to its corresponding time-dependent game, and for going from the corresponding time-dependent game to the corresponding time-independent game. Okay? And the hard part is usually going backwards. But even that is actually known from the time-independent point game to the time-dependent point game in a constructive manner. It is just this last link, which is so far known only to be non-constructive. So you know that if you're given something in the time-dependent point game picture, then there should exist some object, which is some protocol, which actually has very similar properties, but we don't know how to find it. Okay? And the main focus of our work would be to figure out how to convert this non-constructive step into a constructive step. Okay? So let's start with how we discuss protocols. So a protocol, it has been shown, can be described in, so any protocol can be described in this form. So you have three registers, Alice's register, a messaging register, and Bob's register. And the protocol proceeds in the following way. So Alice applies a unitary U1 on her register and the messaging register. And then she sends the messaging register to Bob. Then Bob applies a unitary U2 on his register and the messaging register, and so on, until the very end where they make measurements, 2 outcome measurements, and they discard the messaging register. Okay, and the outcome determines who wins the coin flip. Okay, the variables that we use here are the usual quantum mechanical variables, as I was saying, density matrices, unitary operators, and so on. To be able to talk about the biases, we actually have to consider 2 SDPs, which are semi-definite programs, as all of you know. So P star A, the probability that Alice wins, a cheating Alice wins, is defined to be an SDP on Bob's local state, where you're trying to maximize over all possible strategies of Alice, subject to the condition that Bob is honestly following the protocol, because that's all we know. Okay? Similarly, we can define an SDP for P star B, which optimizes over all cheating strategies of Bob to find what is the maximum probability for Bob winning. And the technique that one uses to be able to move further than just the optimization is to take the dual of the problem. And this gives us a certificate on the cheating probability. So it gives you a bound on what is the best cheating probabilities one can do. Okay? So this is just a very quick overview of how we describe protocols in this particular framework. Now let's move on to the time-dependent point game, where we can actually say a lot more. So a time-dependent point game is actually just, can be thought of as a sequence of frames, where by a frame I mean a collection of points on a plane. Okay? The rules of the game are as follows. You have to start with points at the location 0, 1, and 1, 0, and they both have to have a weight half. Okay? The final frame must be a single point with some coordinates beta alpha. And the claim is that if in the intermediate frames you follow some condition, which I'll describe in a moment, then you're guaranteed that there would exist a protocol with biases P star A less than alpha and P star B less than beta. I'm sorry, cheating probabilities. Okay? And note here, we did not say anything about unitary matrices or operations or anything. It was just by following some rules. Okay? And the technique I'll just mention that is used here is called operator monotone functions. Okay? Where you just generalize the notion of monotone functions to matrices. I will not have the time to explain this connection, but let me explain the rules. So imagine you have ng initial points. I will use the notation g for initial objects and h for final objects if I have 2 frames in mind. So imagine you have ng points initially. Then the rule is that the final point can be as close as the average location of the initial points. Okay, it cannot be any closer. The split is a condition where you're going from 1 point to nh points. Okay, and in this case, one has to preserve the harmonic average. Okay. And finally, if you have a single point, then you can always increase the coordinate of the point. Okay? And remember, we want the final coordinate to be as small as possible, because smaller the coordinate, better is the bias, right? Because the cheating strategies, so the cheating probabilities were bounded by the coordinate of the final point. Okay? Right. And if you have, in general, ng points, and you're going to nh points, then this is a slightly complicated looking condition, but you can see you can verify it. Okay? Okay. So let us try to use these 3 and try to construct some protocols, or at least some point games, for which we know there would exist protocols by the claims made by the framework. So we must start with these 2 frames. This is the initial frame, that's the final frame. And we can start with raising it, for example. Okay? And if we raise it, after that we can merge it. Okay? To get a single point at the location 1.5. Okay? And this should remind you of a protocol that we discussed in just a minute, like a few minutes ago, which was the flip and declare protocol. Because remember, Alice could cheat with probability 1, and Bob could cheat with probability half. Okay? So by just following these simple rules, you've already constructed a protocol that we considered in the beginning. But of course, it's trivial. So the question is, can you do something better? And if you note, we did not use the split. right? We just used a raise and a merge. What if you use a split? Well, it turns out that if you use a split, then the final coordinate, so if you use a split here, you raise, you merge, and then you merge again, then the final coordinate you can get is 1 by root 2 and 1 by root 2, okay? And, well, congratulations, you've essentially published a PRL, because this was a result which was published in PRL back in 2002. And of course, it was not done using this framework. So that is the power of this framework. Within a couple of seconds, you've been able to prove a very important result. And actually, if you recall, strong coin flipping was shown to have a bias which actually matches the bias of this particular protocol. Okay, so at that point, it wasn't even clear if you could do something better with weak coin flipping. Okay, so one split already gave us an advantage. What if we use more splits? Right? That's the obvious question you ask. And this question was answered by Motion, and in fact it is this, in the limit of taking infinite splits and following a very similar scheme, one can get a protocol which has a bias which is as little as 1 by 6, showing that weak coin flipping can in fact be done better than strong coin flipping. Okay? Okay, so this completes a very quick tour of what a time-dependent point game is. Now let's try to understand what a time-independent point game is. Okay, and this I'll do a very brief, I'll just explain it very briefly. So the idea here is that instead of considering a sequence of frames, you consider differences of frames. And when you do that, you have to allow for negative weights. Okay? And the advantage of doing this is that in the end, instead of considering a large number of sequences, you can consider just 2 functions which have to satisfy properties similar to the ones that I described earlier. Okay? And that's all that I will say about it. The claim is that if you can construct an object which satisfies these properties, then there exists a corresponding time-dependent point game with the same final coordinate, with the same bias, essentially. Okay? And the claim, the technique used here is called a catalyst state. Okay? This is something that I'll come to a little later, but just to mention it. Why I mentioned the time-independent point game is because it is in this framework that Motion constructed his Motion proved the most fundamental result about weak coin flipping, which is the following statement. He constructed point games where epsilon is equal to 1 by 4k plus 2, where k is just the number of points that appear in the non-trivial step of the game. Okay? And as you can see, if you take k arbitrarily large, epsilon can be made arbitrarily small, okay? Which is exactly the statement that weak coin flipping is possible, arbitrarily well. Okay. For k equal to 1, we get the epsilon to be 1 by 6. It's easy to see. And we already have an explicit protocol for this. However, we cannot go back from the time-independent point game to the protocol directly because of that non-constructive step. Okay? And this is where we make a contribution. So we, in fact, give a framework which we call TEF, a time-dependent point game to explicit protocol framework, because I didn't expect to be presenting it here, so it's a very strange name, but okay. So the idea here is that you can construct a protocol if for each consecutive frame of a time-dependent point game, one can construct a unitary which satisfies the following 2 conditions. The first condition is a matrix condition. Hi and Gi are just orthonormal basis vectors written in some funny notation. Xhi encode the coordinates of the final points of the frame, and Xgi encode the coordinates of the initial points in the frame. Okay? And one has to satisfy the vector, the vector equality, which is which encodes the coordinates, the weights of the initial points and the weights of the final points, as described. Okay, so the unitary has to satisfy these 2 conditions, and if you can find a unitary which satisfies these 2 conditions for every consecutive pair in the sequence of the time-dependent point game that you're given, then the claim is you can find a protocol explicitly. Okay? And I will use the notation V and W for denoting the initial and final states, okay, which contain the probability weights. Okay. So for the dib-dib-boom protocol, remember that we just used split and merge, essentially. There was a raise somewhere, but the main steps were the split and the merge. And the claim is that if you use this innocuously simple-looking expression for the unitary, which is W goes to V and V goes to W, and identity and everything else, it turns out that it's already enough to implement the split and the merge, which is to say that the aforesaid conditions are satisfied for this particular unitary. And why we are interested in this is because it lets you, at least to the best of my knowledge, for the first time convert the point game of the currently best known protocol into an explicit protocol. Okay? And encouraged, we wanted to see if we can do better. Because we know the point game for the 1/10 game, and for that, we need the catalyst state. Remember, because I mentioned the time-independent point game, the technique used was the catalyst state. It turns out that to construct the catalyst state and for other initialization purposes, it's enough to be able to do the merge and the split, which we already know how to do. The non-trivial part here was to figure out how to implement the 3-to-2 moves, which I have highlighted. I hope that they're visible. The 3-to-2 move, for which also we were able to find an analytic unitary. The expression is not pretty, so I don't give you the full detail here, but you can look it up in the article. And the 2-to-2 moves, which were involved in this transition. Okay, and we also find a unitary for this. So effectively, this means that we have been able to construct a protocol which is better than the 1/6 bias protocol, which was due to Moshaw back in 2005. But then, of course, we still know that we should be able to do better than this, because we know that epsilon can be made arbitrarily small. So how do you solve that problem? So the thing over here was that the unitaries that we constructed were based on heuristics and numerical simulations and things like that. So we didn't have a systematic recipe. And we wanted to find such a recipe. So to be able to do this, we note that we have, so to go back from the time-dependent point game to the protocol, so to just quickly remind you of what's happening, we constructed this framework called TEF for reasons I would not like to discuss. And it worked so long as you could satisfy these two constraints. You could find a unitary which satisfied these two constraints. It turns out that you could write those constraints in the following form. So you could write it as having two matrices, xh, which has as diagonal entries xhi, the coordinates of the final points, and as diagonal entries of xg would be the coordinates of the initial points in the frame. And you have a very similar, essentially the same vector condition, uv goes to w, where v encodes, let me remind you, the initial weights, and w encodes the final weights. Okay, so you can rewrite it in this form. This form is actually quite useful because it admits a very interesting geometric representation. So let us imagine that you're restricting yourself to real numbers so that all unitaries become essentially orthogonal matrices. Okay. Now, if X is a diagonal matrix, and you consider the set of vectors U such that UXU is 1, then it's easy to see that the equation I'm asking you to satisfy, where X is a constant and U is the variable, is Xi Ui square is 1, which is just an equation of an ellipsoid, right? So that's my representation of an ellipsoid. And it's not hard to see that it generalizes for any positive matrix X, because it is just a rotation, right? So in this sense, the inequality that I had written is basically just saying that you have an XH ellipsoid, which is the blue one, and the XG ellipsoid, which is the red one, and it is rotated such that the inner ellipsoid stays inside the outer ellipsoid, right? So it's just a geometric containment statement. That's all that we are saying. Okay, so with this picture in mind, let us just assume that the solution is given to us. I know that we said we have to find the solution, but let's assume the solution is known. Okay, so you have an orthogonal matrix which satisfies OV is equal to W and satisfies the containment of the ellipsoid. Also imagine that for some reason, the point of contact is along W, where W, remember, was the vector which contained the weights of the final points. Okay? So that happens to be the case. It is not hard to see that the point of contact for the unrotated XG ellipsoid would be at V, because you see, OV goes to W. We already assumed that, so there's nothing surprising there. An interesting observation here is that the normals at V and W must be mapped to each other. So the normal at V, say it's given by NG, and the normal at W, say it's given by NH, should be such that after the rotation, NG gets mapped to NH, right? Otherwise, there'd be an intersection. Similarly, we can also conclude that the inner ellipsoid must be more curved than the outer ellipsoid at the point of contact, right? Reasonably simple assumptions, deductions. Once you have these observations, it turns out that you can generalize a lot. So first of all, one can show that you do not lose anything by restricting to real matrices. You can generalize the elliptic representation, which is to say that you can always find an equivalence such that the contact point is always along W, which seemed like a very unreasonable assumption, but you can do it. And you can make the notion of curvatures very precise. by considering what are called Weingarten maps. And when you put all of this together, if you're given a k-dimensional problem, and you tighten it, which is to say that you make sure that the ellipsoids touch at some point, and you can check that easily, and you use the reasoning given in the previous slide, you can actually write a k-1 dimensional problem, okay? And you learn a little bit about the unitary. And if you iterate over this procedure, you can actually find the unitary explicitly. Okay, so it's a very high-level overview, and that's all I will give. It's a little bit more technical. But this essentially means that we have solved the weak coin flipping problem. Why? Because remember, the framework that we constructed required us to satisfy the constraint equation for the unitary, which we have now been able to solve using the elliptic monotone align algorithm, which again is called for reasons beyond my own comprehension. So that means that weak coin flipping, we can convert the time-independent point game, which was given for weak coin flipping by Moshe, all the way back into explicit protocols, okay? And that is essentially our results. Let me quickly summarize. We came up with the framework which allows us to construct explicit unitaries for implementing the 1/6 protocol. Additionally, using the moves that we constructed and by constructing certain other moves, which implement the 3-to-2 transitions and the 2-to-2 transitions, which are not a combination of merge and split, which is what was the non-trivial aspect there. We have analytic expressions for being able to implement the 1/10 bias protocol. Finally, we give what we call the elliptic monotone align algorithm as a systematic way for finding these unitaries, so that you can finally construct protocols with epsilon, which is the bias, getting arbitrarily small. To put it in perspective with the previous results, we have been able to improve upon Moshe's result by replacing the 1/6 bias protocol with a 1/10 bias protocol, for which the unitaries we know analytically, and for a bias, for arbitrarily small biases in an algorithmic fashion. And finally, because we have a weak coin flipping protocol which can achieve biases arbitrarily small, we can also implement strong coin flipping optimally. And there are some other results also which can follow from weak coin flipping, such as bit commitment, which I haven't mentioned here. But that is where it stands with respect to the remaining things. So let me quickly end with a couple of open questions. The first thing is the resource requirement, which is something I did not mention, and there's a reason for it, because the best 1/6 bias protocol requires just a couple of qubits and a qubit, whereas for the 1/10 bias protocol, you need an arbitrarily large number as you approach 1/10. There's a very interesting mathematical structure between the solutions, which is to say the unitary matrices one obtains, and the kind of weight assignment which is done on these frames by Moshe. And the relation is that the condition that I said, that the ellipsoids must touch along the W direction, that is automatically true for these cases. And it's not just that, it's true for all subsequent sub-problems. Okay, so that's a very curious geometric constraint, which is not at all evident from the weights that we are given. There might also be some simpler unitaries, which can be obtained by looking at certain other constructions in the time-independent point game framework, which give arbitrarily small biases, which were due to Pelchat and Hoyer. And in all of this, we assume that the unitaries are exactly known, but in any realistic implementation, there would be some noise, which needs to be accounted for. And finally, we would like to bound, and I think this is the most ambitious of all of these, we would like to bound the number of points one needs in the time-dependent or the time-independent point game picture to be able to achieve a certain bias. And the reason for that is that the number of points correlates directly with the resource requirement, which is to say the number of qubits needed. And we would like to know what is the best that we can do. Okay? So with that, I would like to thank you for your attention. And if you have any questions, I'd be happy to answer them.
Okay, thank you, Atul. Questions?
Hi. Is there a point in the game, in this protocol, where, say, one of the, say Alice learns the output bit, but still has time to abort the protocol, so that Bob doesn't actually get to learn the output bit? Or is it the case that they both basically learn at the same time and there's no way to prevent the other person from learning?
Right. So Okay, so what happens is usually if everything is done honestly, if you assume both players are honest, what you end up with is an EPR pair. So you have like a 0, 0 plus 1, 1 state. And now whoever makes a measurement would get some outcome. So there could be one player who measures first, but the other one would always get a correlated answer. Okay, so.
Okay, more questions? Okay, so I'll ask one. So you had in the beginning this hierarchy of cryptographic tasks. Can you use the explicit protocols in your technique to construct explicit protocols for the other things?
I had a hierarchy. So, okay, so there are two things. The hierarchy was basically 3 formalisms which are equivalent. Is that what you were talking about? Or you're talking
in the beginning,
about
the different cryptographic tasks? You had
right.
the different
Okay, so that part I will not be able to answer exactly because it depends on how the reduction is done. So if you assume that you can perform something as a black box, and then you claim that if I'm given this black box, I can implement a certain task, then of course it would be possible because I give you how to construct the black box. But if the other constructions themselves are non-constructive, then I don't think I can make a statement independently.
Okay, thanks.
There's a question at the back.
Hi. I guess you played around with these 3 to 2 and 2 to 2 transitions in the point games. Does it seem like 1 over 10 is optimal?
Well, I couldn't quite understand. Could you please say it again?
Does it seem like 1 over 10 bias is optimal with like 3 to 2 moves and 2 to 2 moves? I'm guessing you played around with them, trying to find the best bias.
It's actually quite hard to be able to do anything better than the 1/6 bias.
Right. Yeah.
And I have tried to see if I can move it around and find some better things, but it looks like it's essentially locked. Like you can sort of get some sort of impossibility results, saying that if you move things a little bit, everything falls apart, which I have not presented because it's not tight. Like it's not a very neat argument, but it looked like a dead end to try to modify it directly. So there's an entirely different way of constructing games where you have a different pattern that you exploit, and that has been given in this master's thesis by Pelchat and Hoyer. So yeah, that's all I can say about that.
Okay, thanks.
You're welcome.
Could you comment on the composability of the coin flip obtained?
Can I comment on the
compressibility?
compressibility?
The
composability.
Yes.
Okay, thank you. That's a very good question. I'm actually myself not entirely sure to what extent you can compose it. You can certainly compose it if you assume that the preferences of the players remain the same, which is to say that so you understand. So if that is the case, it's fine. But if it is somehow the case that for the subsequent coin flips, I can change my mind, then it will not be composable very easily.
So if you're interested in the situation where you only allow a very small number of rounds of interaction, like order 1 round trips, do you know anything about like what's possible then?
So in all of these things which have like smaller biases, so there's actually a result by Ambinis which lower bounds the number of rounds that you need in order to be able to achieve a certain bias. And while I don't remember the exact relation, it tends to infinity as you tend to 0. So.
More questions? No, okay, so let's thank Atul and the other speakers in this session.